So before we start the lecture, we will have 2 minutes, few seconds mourning for one of our fellow student who passed away last evening. His name is Sayant. He is 3rd year BTech Naval Architecture. He met with an accident in the road yesterday. He passed away, so we will just maintain silence for about 30 seconds, then we will proceed with the class, because academic activity in my opinion should continue. So we will anyway pay respect to the departed soul by observing silence for a few seconds, then we will continue. Okay, we will resume with the classes. Now we are on lecture 12 on dynamics of ocean structures. In the last lecture we discussed the derivation of stiffness matrix for a TLP. We said the equation of motion of a TLP is formulated with the classical theory as we understand here. We are talking about derivation of the stiffness matrix. One may wonder why I got to derive the stiffness matrix, because TLP is a geometric design to suit deep waters. So it is a very special type of system which has got hybrid design capability, which is otherwise addressed as compliancy in the literature. Because of the classical separation of two set of degrees of freedom, TLP is able to encounter the environmental loads at deeper water depths. It has been found effective in terms of cost and in terms of performance. So just to understand, if you want to do further innovative geometric design in deep water and ultra deep water systems, let us try to understand from the first principles how do you derive the elements of this equation of motion independently. As we all understand, there is no greater difficulty in deriving the f of t, because we already spoke enough about this in the first module, but still we will focus on m, k in this lecture. We will speak about c in another 2 lectures in detail, how to estimate the the damping matrix for a TLP in detail in the next 2 lectures. So coming to the argument of how do you derive k, we already said Kij will be the stiffness coefficients, where I give unit displacement in the respective degree of freedom in the jth degree and try to find the forces which are initiated because of the unit displacement given the jth degree by keeping all other degrees of freedom constrained. So we derived column by column, the stiffness matrix derived column wise. We understand TLP has got 6 degrees of freedom, so K matrix will be by and large a 6 by 6 square matrix. So we will derive the stiffness matrix coefficients column wise. We already derived K I1, K I2 and K I3 for I varying from 1 to 6, we already said this. So we derived till the 3rd column, that is the heave displacement degree. Now we will talk about roll degree of freedom. So let us recollect that I have a platform whose nomenclature is given like this. So these are the column members designated as 1, 2, 3 and 4. This is the plan, and this dimension is marked as plan breadth, and this dimension is marked as plan length, and of course for the dimensions being equal, this becomes my mass center. I call this as center of gravity. I am looking for the roll motion. This is my wave approach angle, and this is my x axis, this is my y axis. Roll is nothing but the rotation about x axis, which I will see in the elevation from this side. So I draw the elevation of this platform from this side, of course I draw it here. So, this is my elevation actually from this side, this is my wave approach angle, this is my water level, this is what I call as dr, which is my draft for the given platform. And as you see here, this column will be designated as 1 and this column will be designated as 2 from the view here. I want to give a roll rotation to this, which is maybe theta 4. So, now I rotate this body to this way, I am giving rotation about the x axis, which is going to be theta 4. So, initially I have tension in the legs which are T0 plus delta T4, I am using 4 here because of roll degree, T0 plus delta T4. Because of symmetry, this delta T4 and this delta T4 will be equal. If it is unsymmetry, you can use delta T4 prime here because the legs can be unsymmetric also. So, I rotate the platform, so this was my original CG. So, this is my H bar, and of course, of clarity, this distance is actually PL. So, when I rotate this platform without imposing any other displacement, any other degree of freedom, you will still see that the tension in the cable will remain vertical, but they will alter now. So, I call this as T0 plus delta T4 dash, T0 plus delta T4 dash. Now, you see, because of these columns getting emerged more and this column protruding up, there is a shift of buoyancy from the left to the right. Okay. So, let us mark that new buoyancy as a point here which is going to act anyway upward, and I call this distance from the CG to the new center of buoyancy as E4. 4 stands for roll degree. E is the eccentricity of the CG. Initially, for a perfect balanced system, the CG and center of buoyancy will remain same. When I rotate or when I tilt, when I give a roll angle to it, now the buoyancy is shifted. Okay. Now, I call this distance as S1 and this distance as S2. So, S1 is nothing but PL by 2 plus E4 and S2 is PL by 2 minus E4. And as we understand, for the tilted position, if I mark the CG and I call also this as H bar. Okay. So, H bar is just shifting as it is. So, either I measure H bar for initial position or for final, it is going to remain same, and of course, this angle is what I am interested now is my theta 4. Okay, this is what I have tilted. And of course, the force generated will be, I am marking it here, which is K44, because that is a force now get generated as a moment because of the theta given. Now with this convention, let us say K14 is the force in the surge degree because of rotation given in roll degree will remain 0 because surge is not affected at all. Similarly, for a unidirectional wave, because the wave is acting only in the x axis, surge force will remain 0, therefore there is no effect of sway because of roll angle, this also remains 0. Now change in pretension in each leg. Remember, each leg can have n number of tethers. Okay, the number of tethers are not counted here. They are not counted here. We are talking about each leg. Each leg can have 4 tethers, can have 6 depending upon the system. So we are talking about pretension in each leg. Leg means I am talking about the column. Call this as delta T naught, sorry, delta T4, which is caused by, that is the initial tension I have in the legs, which is now going to be PL by 2 cos theta 4, that is the component in the direction of delta T4, which will remain same as delta T4 naught also, or delta T4 prime, it is going to be same. Now what is the difference between delta T4 and delta T4 prime? Delta T4 is the change in tension or change in pretension in the nearer leg. Delta T4 dash will be the change in pretension in the farther leg. But in this case, because of symmetry, all the legs are equidistant in the roll dimension. This is my roll dimension PL. So consider leg 1 and 4, it is PL by 2, consider leg 2 and 3, it is again PL by 2. Therefore the change in tension in the near and far leg will remain same. If you have a geometry which is not symmetric in plan, then you can handle this separately. Okay. So let me now derive K34, which is the force in the heave degree because of the roll angle given at 4. The force in the heave degree will be affected only by the change in tension, that is now causing the disturbance, is it not? Which will be 2 times of P4 plus delta T4, of course divided by theta 4, because the unit is Newton per meter or Newton per radian. Now I know theta 4, delta T4. I know delta T4 and delta T4 dash from this equation. You may wonder how do I know that, because delta T4 is a function of theta. I am going to come to that later after I discuss my derivation. For example, if I know theta, I can find delta T4 because all other components are known to me, it is a geometric dimension. So delta T4 and delta T4 prime are known to me, therefore K34 can be computed. Okay. Talk about K44. Any questions here? Remove this. That will be affected in delta T4 automatically. K44, which will be the force in the roll degree because of displacement given in roll degree. So I can say K44 of theta 4. So look at here, K44 is what is happening here. This has got to be counteracted by buoyancy into E4 plus this change in tension of S1 minus this change in tension of S2. Okay, I am taking moment about the point where I am rotating the platform. So I should say easily FB of E4 plus 2 times of S1 minus E4, that is my eccentricity, plus minus 2 times of S2 plus E4. So, this 2 stands for the set of legs of 1 and 4, this 2 stands for the set of legs of 2 and 3, or alternatively this positive value stands for set of legs of 2 and 3 because that is coming from here, and the negative value is coming from here which stands for the leg of 1 and 4. Now, here instead of computing S1 E4 and S2 E4 separately and then working out K44 directly, alternatively I can also write K44 like this, which will be pi d square by 4 of 4 times of the 4 column members which have been immersed, rho w of g of sin theta 4 of PL. Okay, let me write it like this, PL sin theta 4, because you can easily find the E4 value from this figure. If you try to plot this separately, E4 can be, look at here, this is my E4, this remains my H bar and this is my theta 4. Okay, I can easily find E4 from here if I know H bar, which is a function of course theta. So, PL sin theta 4 will be the component on the vertical direction which is causing my buoyancy force, plus 4 times of T naught H bar of sin theta 4, that is nothing but E4. I am separating this out equally, I am separating this out E4 and S1 separately from here, of course by theta 4, because I want this as K44 as a force unit, this is already in force units, plus I have separated this E and negative time separately, I have taken it out, so plus 4 times of theta 4 of AE by L of PL by 2 cos theta 4. This is nothing but delta T4. Already have an expression in the previous, I rubbed it off, is nothing but AE by L PL by 2 of cos theta 4. We already have it here. So, K44 now there is no theta 4 here, it is already a force unit. AE by L of length, it is already a force unit. So, K44 can be easily computed if I know the value of theta 4, remaining all are known to me. DC is known, density of sea water is known, G value, H bar, T naught are all known to me. T naught is the initial tension given to the theta, all are known to me, compute K44. So, now I have K34 and K44, remaining all members are and all coefficients are 0 for the roll degree. Similarly, if you draw the same view with the front direction and give a pitch angle, except replacing this column as 1 and this column as 4, remaining all will remain same, there is no change, except that this will become theta phi, this will become K phi phi and so on. Okay. So, similarly for pitch degree of freedom, I should say K1 phi is set to 0, K2 phi is set to 0, because there are no forces in surge and sway activated because of rotation given in the pitch degree of freedom. K3 phi looking at K45 I mean K34 same way I am writing nothing but 2 delta T phi plus delta T phi naught by theta 4, that is what we wrote for K34 also. So K55 the same manner just now we wrote for K44, so it is going to be 4 pi d square by 4 rho Wg. Here I am using Pb sin theta 4 because this dimension is Pb plus 4 by theta phi of T naught h bar sin theta phi plus 4 Ae by L of Pb by 2 cos theta phi. This is how I get my K55. So I got the fifth column of the stiffness matrix now. Let us talk about the yaw motion. I will remove this. In yaw degree of freedom, I will remove this. So yaw is rotation about the plan. Let us say I am rotating about this axis, about z. Okay. So let me draw in plan itself. So this becomes my column 2, this becomes my column 1, 3 and 4. This is my theta 6. I am rotating about the vertical axis, the z axis. So obviously the force required to rotate this is what I am trying to measure, which is K66. Now imagine I have got a floating body, let us say imagine I have got a floating body like this, which is rectangular in shape, maybe square. So see from there, this is my Pb, this is my Pl, this is my wave direction. There is a Cg in this body somewhere here, which I am marking it here. There is a draft for this box somewhere here, this is the water level or sea level. I am trying to, there is anchored by the sea to the sea bed with the teethers. Okay, now I am yawing this. So initially it was horizontal, it was straight, I am yawing this, I am giving a clockwise rotation which I have done here. So I am yawing this, you will obviously see that the position of these teethers will get twisted, okay, tension will get changed, but there is no absolutely there is no going to be difference in my Fb value marginally because of only the T naught delta T6 happening in the teethers. Okay. So there is a component, initially the cable is straight, now the cable is twisted, there is a component which is going to be L dash, the new length of the cable. Initially the cable was L, now I have twisted, it has become L dash, which is a combination of L and theta 6, is it not, combination of theta 6. I want to find L dash, the change in length of this cable will be L dash minus L, is that clear? So that is what I am going to do it here. Yeah, it will be. So let us say the new length L1 is of course the square root of sum of the components which is original length plus the effect of shift of this twist because of theta 6. I mark it slightly in a different way, I say that this point which is now twisted, I am just pay attention here, this point from here I am marking as A, and this point from here I am marking as B. Once I know these two components, I can write this as theta 6 square of A square plus B square. Is it okay? So, once I know L1, delta T6, which is the change in tether length, tether tension now, is going to be simply AE by L of L1 minus L. There is a new tension now which has changed in my tethers. So, I remove this. So, force in such degree because of yaw rotation is 0, nothing is happening in surge, it is identically rotating only in the horizontal plane, okay. Nothing is happening in the surge axis. Obviously, for a unidirectional wave, sway is of course 0, we do not have this with us. What can you say about K46 and K56? 0, because for 4 roll means because K26 is 0, is it not? Sway is 0, therefore pitch is 0. Similarly 0 because K16 is 0. So, what I will have here is K36 and K66. So, K36 into theta 6, again in the heave degree, the force which is given to the system will be from the change in tension and the original tension of the cables or tethers. Okay. So, I can simply say it is going to be 4, there are 4 legs, T naught L by L1 minus 1, that is the change, plus 4 delta T6 which I know here of L by L. So, I will get K36 now. Of course, knowing the value of L1, I can substitute them and rewrite this equation in a different form, that may not be required now. Let us try to find K66 of theta 6. Which is going to be the moment of these forces. Now, what happened when my cable is vertical, when my cable is normal to the board vertical, it is extracting force only in the vertical direction. Once I have yawed this in plan, this will now create a moment, okay, because of the twisting action on the tethers, which I can indicate vectorially as delta T6, as delta T6, okay. So, now I can write K66 as 4 times of T0 initial tension plus delta T6, the change in tension. How much it has changed? Because of A square plus B square by L1 of theta 6. So, this goes away, K66 directly given by the change in tension and the moment of this about the point of interest. Having said this, we can now write the stiffness matrix in a complete form, which is 6 by 6 column wise. We write column wise. For example, this value will come here, because this is 1, 2 and 6, this is 1, 2 and 6. We have derived all of them column wise. We got K160, K260, 46560, this and this we have, we derived column wise, that is what we are having here. Similarly, we derived all the coefficients column wise. Now, let us see what is the beauty about this particular matrix. You look at this matrix now, we have K11, K31 and K51, similarly 22, 32 and 42 and so on. There are many observations we can make from this matrix. One, the matrix is a square matrix, but it is non-symmetric. Okay. K31 is present, but K13 is not there. Okay, it is non-symmetric matrix, of course of size 6 by 6. It means this matrix cannot be banded. If you want to analyze this problem, you must handle this matrix as a full size matrix. You cannot band it because it is non-symmetric. That is the first observation we can make from this. Look at the third row of this matrix, that is K31, K32. It means the effect of heave caused by all degrees of freedom are predominantly seen in the problem. You give unit displacement any degree of freedom, surge, sway, etc., heave responds to it automatically. So, this very clearly shows that heave has got a very strong coupling with all degrees of freedom. Okay, whatever movement you give, heave will be activated automatically. That is why we call this platform as heave restraint system. You try to move this platform in any manner you want in the 6 degrees of freedom, heave will restore its position automatically. That is the beauty of the geometry. So, heave has got a very strong coupling with all degrees of freedom. That is the second case we see, because mathematically the third row is present always. Okay. So, mathematically we can see it is a strong coupling. Further, you will also note that the off diagonal terms, for example K3151, K36, K35, K42, off diagonal terms show the respective coupling of each degree of freedom with heave. Okay, they show the respective coupling. Most interestingly, pick up any one coefficient. For example, let us say we pick up this coefficient K36. Okay. K36 depends on the following. It depends on T0, which is known to me for a given system, because it is initial tension given to the system to afloat in the sea. So, T0 is known to me, but delta T0 is the dynamic change in tension because of the rotation or because of the degree of freedom you are giving, whereas delta T6 depends on the value of theta. Okay. So, what you can see here is K coefficients depends on the response. So, the stiffness matrix is response dependent. Okay, it is a unique problem in this geometry. Generally, stiffness matrix is a material or a section characteristic. For example, AE by L, axial stiffness of the member. Okay, A cross section area, E Young's modulus, the length of the member, you know the axial tension given in the member. It is never response dependent. For example, 4 EI by L, bending stiffness. Okay. So, there is no displacement component here. AE by L, axial stiffness, there is no displacement component here, these are all fixed, does not change. Okay. Whereas, in this geometry my stiffness coefficients are all response dependent. What does it mean? This is having a very classical problem in solving this. See what is that? Look at the equation of motion here. Okay, let us look at the equation of motion here. Let us not focus on any of the terms except K and F of t. Okay. F of t we already know, because of the compliancy or because of the lateral movement of the platform, it is response dependent. If you look at the force vector, okay, if you look at the drag component of the force vector of Morrison equation, you will find there is a component of velocity or let us say displacement of the platform in the wave direction. Okay. So, F of t is function of x of t, is a function of x of t, and K is also a function of x of t or theta of t, whatever you call. Okay, you cannot solve this problem actually, because you know it becomes iterative. Okay, the left hand side and right hand side are strongly coupled. It means it is a classical problem of dynamics where you cannot decouple the equation of motion. You cannot decouple the equation of motion, you have got to handle this equation of motion as a total solution. Okay, it is a very classical problem imposed by the geometry, because the stiffness matrix is response dependent. That is a very classical problem here. The next problem is the stiffness matrix is also non-linear. Where the non-linearity coming from? They depend on cos and sin components of your displacements, which are non-linear. Of course, non-linearity also comes from f of t. There is a square drag term here, which is also non-linear, but stiffness matrix also has got non-linear terms inside the problem. So it is a non-linear classical dynamic analysis problem which cannot be decoupled. Okay, it is a very classical problem. This problem has arisen because of the geometry. I am not talking about m, I did not speak about c yet, I am only talking about k. K is actually a system property, m is also a system property, but k is predominantly a system property, is it not? So just looking at the system itself, I understand the system depends on response and system depends on non-linear coefficients of the response. Okay, so it is a very classical problem. So how to solve this issue, that will come later, that is what we are addressing here. It is non-linear, and most importantly your values of theta 6 a, b are all dynamically replaced. So it is a function of time. So stiffness matrix is not constant, it varies with every instant of time. This is again another problem posed in this geometry. Okay, you cannot simply ideally take one stiffness matrix and solve the problem. K is going to dynamically vary throughout your length of the solution. Okay. So these are interestingly discussed by different researchers. I have given a very brief reference of 2. When I finish this lecture, I will give you about, let us say, 26 to 30 references who spoke about all these non-linearities and the solution procedures in detail later. Okay. Now in this equation of motion, we have believed to understand that how to derive a stiffness matrix. Okay. Because this is a classical derivation which is not available in standard textbooks. Okay. We are talking about research papers now. We are given the references. Morgan and myself, we did a lot of work on this. So you can refer to these papers available in different international journals. So it is basically a fundamental derivation what we did for the development of the geometry. Okay. Now let us see what is the complexity in M matrix. The mass matrix also has difficulty in this problem. Let us see what is that. Is there any questions on the stiffness matrix? So derivation of mass matrix. So mass matrix is again going to be a 6 by 6 matrix because it is a rigid body motion. We assume that the structural mass is lumped at each degree of freedom. So it is a lumped mass problem, it is not a continuous variation problem. Okay, it is a lumped mass problem. The moment I say this, what is that instantaneously get into my mind? When I lump the mass at each degree of freedom, maybe single degree, 2 degree, 3 degree, when the mass is lumped at those degrees of freedom, what do I immediately get in my mind? Yeah, very good. So mass matrix is supposed to be a diagonal matrix, but it will not remain diagonal in this problem, that is the catch here. I will show you what are the difficulties here. So it should remain diagonal, but it will not remain diagonal. I will show you what are the problems. So the mass matrix is expected to be, I will write the mass matrix here. The mass matrix expected to be a 6 by 6 square matrix so M11, M22, M33, no problem here. These are all nothing but M11, M22 and M33 are nothing but the total mass of the system which is added in all degrees of freedom respectively at surge, sway and heave degrees. M44 will be the mass moment of inertia about x axis, which is nothing but m times or M11 times Rx square. Similarly, M55 and M66 will be respectively Ry square and Rz square. You can compute Rx square easily from this problem because it is I by A. You can easily find out the value of mass moment of inertia of the whole system with respect to the mass center, and you know the cross section area of all the members, you can easily find Rx. Okay. So, one will know all the diagonal values of this. What will happen to me off diagonal terms here? Okay. So, I have one off diagonal term which comes from plus MA11. I call this A because it is added mass term. So, I remove this. So, the MA11 term which is due to the added mass, which can be given by pi dc square by 4 of the difference of Cm minus 1 of x double dot surge rho multiplier is there. I have MA51 also, M additional mass phi 1 . Now, look at the plan here, this is my plan, these are my axes, this is my x axis, my y axis, this is my wave direction where the wave is hitting the platform. I have an additional mass in such degree, this additional mass will create moment about y axis, that is my A51. Okay. So, A51 moment of MA11 about Cg. I will also have MA33. MA33 is the added mass term in the heave direction, which is again pi d square by 4 rho w psi m minus 1 of heave x double dot. I am talking about mass into acceleration. I will also have MA53 how MA53 is coming into play? Because of the differential heave, there is a probability that some of the columns may get immersed lesser, some of them may get immersed more, 1. 2, because of the wave approach, the crust may sit here, the trough may sit here, there is a variation in the buoyancy between the legs. The moment of that heave displacement about the axis is what MA53 is. Okay. I am not talking about unidirectional, I am not talking about multidirectional wave. If you talk about the wave in every angle, then all other factors will also get filled up automatically. I am talking about a unidirectional wave. So, therefore, I get MA51 and phi3. Can you tell me MA33 is coming from a specific concept of TLP, what is that? I want the technical term of this. Ma33 is arising from dash. Is an additional mass moment of inertia because of variable submergence effect. Set down, very good. So, it is because of set down, okay, because of set down effect. So, therefore, you can see here the mass matrix is also not diagonally dominant. You have got off diagonal terms which will explain the coupling of this with respective degrees of freedom. So, we spoke about stiffness matrix, we spoke about mass matrix. We will speak in detail for 2 lectures about the damping matrix, because it is very important how one can estimate the classical damping and non-classical damping for offshore structures. It is very important. There are different models we will discuss. One is we will talk about the Rayleigh damping model. When you talk about damping, we talk about Rayleigh damping model, we talk about Kahi damping, we also talk about superposition of modal damping. All these are classical damping. So, we have to explain all these things and do problems on each one of them and estimate the C matrix actually. Now, remember importantly, C matrix of course is a function of M and K. And K is dynamically varying. So, C will also have this complication. Okay. And since M has off diagonal terms and keeps on varying, because set down depends on what is the wave height and what is the motion of x. So, M will vary. When M varies and K varies, omega varies. So, even the classical theory of percentage damping to critical will also not apply to this problem, because omega keeps on varying. Okay. When the frequency varies, mode shape varies. When the mode shape varies or the value vary, the damping ratio is respect to critical, because it is 2 zeta omega m. Okay, omega and m varies. So, you cannot actually fix C so easily with this problem. So, in the equation of motion you have got every element given except x, x dot and x double dot, which are unknowns for this problem, remaining all are a complication by itself. So, when you attempt to do any geometric innovation for any platform or any design of this order to cater to any specific design requirement like compliancy in this case etc., you will develop a very high nonlinearity and high complexity in solving the equation of motion. So, every new innovative form developed for offshore structures for ultra deep water etc., will have this complication inherently inbuilt in the system. So, you must know the fundamentals of solving this, otherwise you will not be able to generate the system problem. Alternatively, one can model this in software and try to solve either in frequency or time domain iteration analysis and get the solutions, but you will never know, or the software will never print at any instant of time what is your mass, stiffness and damping matrices. It will never print. You talk about any software, it will never give you instantaneous values of K. You cannot debug the software while running and find out at t is equal to let us say 5 times the delta t, give me a K value, it will never give you. Therefore, you will not be able to ascertain the stability of the platform in any point, because K and M govern stability of the platform actually. Okay. When you have these problems in certain with you can always find out what is the difference in the coefficient variation in K at any t from 0 to 10 seconds, and for that maximum variation you can check the stability of the platform also. Okay. Unless otherwise you know how the coefficients of individual components of M, C and K are derived, you will not be able to do this. Okay. Therefore, strongly and many researchers have attempted and proved in the literature that for compliant structures of this order, standard solutions from software are not acceptable. So, you have got to do an analytical study, not a numerical study. Analytical study is you have got to write the equation of motion, you have got to input k, m and c in the time domain and iterate it and find the solution. So, there are two inferences I gain from this problem. Whenever I touch to interfere with my geometry to gain advantage, the disadvantage is I am landing upon high complexity of mathematical solution procedure, number 1. Number 2, I cannot take this problem back to the existing coding or a numerical study and model this. Yes, solution will be available, it will give you the time history, it will give you the video also. As far as many high end softwares are concerned, you will never know what is the variation of k and m in the whole period of 10 or 20 seconds of iteration, you will never know this. Okay. So, if there is a fundamental question of talking about any let us say stability issues or talking about installation problems or talking about let us say earthquake analysis on these structures or talking about the pull out possibilities of tethers, because when k exceeds or when AE by L exceeds the ultimate limit of the member, there is a possibility the tether can pull out from the structure. You will never know all these values, and above all fatigue analysis for tethers cannot be done if you do not know these values, because it has to quantify the variation in the force in the tethers. So, if you do not know them, because delta T0 you will never ever get from numerical analysis, never. So, you have got to write a coding on this, okay. And the coding has got other mathematical problems. If you look at the M matrix and K matrix, it is not a guarantee that the K and M will be always diagonally dominant. So, your solution may work out for certain bandwidths of T and it may become non converging for certain bandwidths of T. So, it is very critical, even analytical studies also not that simple, okay. You cannot write a solution problem for this, so that you can always find. You may wonder that you will never get even omega value for a given k and m at any time t is equal to phi delta t, you will never have this value. So, in such situations how people have solved these problems. So, there is a very interesting scheme given by Newmark's beta. So, we will talk about that scheme and then we will explain the solutions. Before that I want to spend couple of lectures totally and dedicatedly on how to estimate the damping matrix, where damping matrix has always been a nightmare for offshore structures in many form. I have picked this example because I want to show how damping matrix of this order of a classical damping can be applied to a new form of this type, then what optimization has been achieved in this I will show you in my next lecture. For a triangular, for a rectangular shape of a square shape I got a value, I have optimized the geometry for a triangular shape. Instead of 4 legs I picked up only 3 legs, because you will all agree in engineering perspective triangle is the basic form of stability. Square or rectangle is a redundant form of stability. I can divide this into a triangle, still it can remain stable. For example, tripods, camera stands all are triangular. For example, the video stand here, there is no 4 leg for this. So, stable platform need to be only 3, okay. So, if you remove 1 leg from here I will save cost, okay. So, it is very easy for me to optimize this, which we have attempted and we have a patent on this. So, I will show you some results on that later once we understand how we do for a square geometry. Then think of any other innovative platform and innovative number of legs which will take this platform to further deeper waters, okay. Introducing ball joints, introducing hinges on the legs, introducing tension buoyant leg platforms at the bottom, introducing extra buoyancy chamber. Think about all these complexities and try to understand how complex it will become when you try to solve the equation of motion. We need to know this because the dynamic analysis has to be done for finding out the time history solution of my problem, okay. And interestingly, if you do not know the values of k and m at a fixed point of time, you cannot find f of t also, okay, because f of t does not only include the wave value, it also has effects of sloshing, slamming, etc., which all depends on the immersion depth, which is nothing but dr in my problem, and dr is counter affected by T0. T0 counterfeits K. So, the complexities keep on increasing in all segments of equation of motion, is it not? How this is attempted, and what is the idealization which we should strictly follow to start with. So, as you understand, many researchers attempted this problem, but they would have posed serious idealization while solving this problem. This idealization is posed because you do not think they do not have a capability of solving all the problem, that is not the reason. The problem is the difficulties are of manifold. You have got to idealize certain values to achieve the optimum value in your response. That is why you will see many researchers have attempted different idealizations in solving this problem. And for that instance, any new innovative form will always start with only basic assumptions and idealization, which are actually the research areas. Okay. So, we are not going to demonstrate how this solution was done using a software. We will give you the results. Of course, the results are always open in all the references given in otherwise in NPTEL website. So, my request would be, if you really want to understand the fascinating problem of this order, please read all these papers before you come for the next class. You will understand actually the complexity of solving this equation of motion. So, next 2 lectures will be dedicated totally on how to estimate damping matrix using these concepts in general. Then I will apply this concept one by one to a TLP and find C matrix for a TLP. So, I have M, I have K and I have C. Of course, I believe you know how to find F of T. We will solve the equation of motion, check for its stability, Matthews stability, and then geometric optimization and apply seismic forces on this and end the discussion on TLP at that point. Then we will pick up one more platform which is further innovative on this, taken for ultra deep waters, which is a triceratop. Talk about again K, M and C derivation on triceratop, apply these problems and show you experimental, analytical and numerical results for a triceratop, which is completely not available in any literature as on today. All will be done based on first principles, which we will discuss it here. So, I think that will end my second module lectures. I must have ended my second module lecture today, because 12 is the number of lectures I have given for second module, but I will require at least another 4 more lectures. I will take it to 16. So, I will compensate this number of lectures in the third module. Third module is slightly faster, because that is going to be on the stochastic dynamics and model analysis. We will expedite it, because we will be an expert at that time to understand most of them what we will discuss. So, we will slightly fasten it and make it more interesting.